So let's see, from our heuristic construction that we were using at the beginning, we can say we can derive this theorem that is very important in many applications. So the bounded function f is integrable in AB if and only if there exists a sequence of partitions Pn such that the limit when n goes to infinity of L is equal to the limit when u goes to when n goes to infinity of u with respect to Pn. Okay, so this is the idea that we can take this regular partition with between a and b, with the width of this interval is b minus a over n, and we can take the limit when n goes to infinity. This partition is going to be refined and refined and refined more and more and more, and the limit of the lower sum will get to the supremum, while the limit of the upper sum will get to the infimum. Okay, so if both things are, so this is going to be equal to the supremum of with respect to all partitions of L, and this is going to be equal to the infimum with respect to all partitions of U, right? So if those things are the same, this is going to be integrable. Okay, and then with that, you can, I leave you to do it at home, to transform what we have done. Well, example 10.1 is the integral of x squared between 0 and a, right? This function that we had integrated before, right? So to do it using this result. Okay. We're not going to get into which functions are integrable and which are not, okay? Because that's a long story, right? But for practical purposes, there are a couple of results that are important. The first one is if f is continuous, then it's integrable, okay, in AB, okay? The idea is, of course, that given a partition, right, you're going to have the lower sum is going to have the sum from k equals 1 to n of the minimum at k, right, between k minus xk minus 1, and the upper sum is the sum between k equals 1 and n of the maximum, right, xk minus xk minus 1. So the how to say this, that the idea behind Riemann's definition is that we have to find, for instance, that let's use a partition Pn, right? And so the limit when n goes to infinity of the difference between this and the lower sum, right? This has to be 0 if f is integrable, right? This is the idea behind the definition. But what's this? Well, this is the sum from k equals 1 to n of nk minus small nk times this, right? xk minus xk minus 1. Well, the idea here for, let me say this, for a continuous function is that the difference between the maximum and the minimum, okay, can be as small as we want, okay? So as we reduce or narrow the intervals, right, this distance between x and x minus 1, xk and xk minus 1, the distance between mk and mk, capital MK and small mk will be getting smaller and smaller and smaller, okay? And that means that in the limit this will go to 0, this difference, okay? That's because that property of the continuous functions, okay? Similar result is that if f is monotonic in AB, then it's integrable in AB. So for instance, if we have a partition Pn, right, if f is monotonic, let's suppose it's increasing, right? So the sum from k equals 1 to n of the minimum, right, times xk minus xk minus 1, and then uf Pn is the sum of k equals 1 to n capital A, right? Right, mi in a monotonically increasing function, right? We had seen before, this is not monotonic, sorry. A monotonic increasing function in an interval mi, it's going to be f at the well, xk in this case, sorry, it's k, this is k. And this is going to be f at the leftmost value, xk minus 1, and the maximum is going to be f at xk, right? So this is f at xk minus 1, this is f at xk, right? So if we compute, let's see, the limit, or, well, and so this is again, fk minus xk minus 1 is b minus a over n, okay? We know that. So if we compute the limit, right, of the limit when n goes to infinity of u fpn minus l fpn, this is going to be the limit when n goes to infinity of the sum, and so b minus a goes away, right? So b minus a and over n, right? Because this doesn't depend on the index, right? So then we have nk minus nk, which is f at xk minus f at xk minus 1, and this is a telescoping sum. So this, if you do it, you get this is f at xn, which is f at b, minus f at x 0, which is, this is b, right? And this is a. So this is f at b minus f at a. Okay, so let me rewrite all of this as f at b minus f at a. But now f is bounded, right? So fb minus fa is a finite quantity. B minus a is also finite, so you have this goes out of the limit. The limit when 1 over n goes, so when n goes to infinity, sorry, of 1 over n is 0. Okay, this limit is 0. Okay, so that's the result for monotonic functions.